Tito, Federico?
Yes.
Okay. So Maria, maybe okay. So Maria, if you want, we can start. It's okay for you?
Yes, it is.
Okay, sorry for being late. Good morning to everybody. So today we have an organizer of this series of seminar, Maria Strazzullo, and she will give that is a last year PhD student under the supervision of Professor Gianluigi Rozza, and today she will talk about driving nonlinear bifurcating phenomena by optimal control, the application to Navier-Stokes equations.
Okay, thank you, Emanuele, for the introduction. You have already read the title, so basically I can skip to the second slide of the talk. First of all, I want to thank my collaborators because they helped me through this, let's say, journey, the journey of this work. First of all, I want to thank my advisor, Gianluigi Rozza, Professor Gianluigi Rozza, my co-advisor, Francesco Ballarin, and I would like to really thank Federico Picchi, who basically introduced me to this magic world of bifurcating phenomena, and we had a lot of fun doing this work together. Our paper now is online on arXiv, so basically if you want to read it, you can download it, and I want only to advertise to Python-based libraries that we are developing in CISA, and all the test cases are coded through these two libraries that deal with parameterized PDEs. So if you want to play with PDEs and parameterized PDEs, you can basically download them or run them on the website. Now, let's go through the outline of the talk. The talk is essentially divided in 4 parts. So we have some motivations about this work, and then we will move towards the general framework we are working with. So optimal control and bifurcating phenomena and algorithms to understand the nature of this bifurcating phenomena. And there is the third part of the talk that is basically numerical tests. Numerical results is the biggest part of the talk, but I want to stress them because they will let you understand the features of this very complex system. And only in the end, I will talk about reduced order modeling for this kind of problems. So let's start by the motivations. When we were talking about this work, the first thing that came up to our mind was the Coanda effect in the mitral valve. So basically in your heart, there is this valve and the blood flows in this valve. And the medical doctors are really interested in simulating this kind of phenomenon. So the blood that flows in the valve. And geometrically, it is quite simple in the sense that the valve can be represented by this domain that is called expansion channel, sudden expansion channel, because the valve is represented by this smaller thin channel and then it expands. You have an inlet velocity here, and the blood is basically described by Navier-Stokes equation. This is steady Navier-Stokes equation parameterized to with respect to a diffusivity parameter, in the sense that this parameter represents how strong, let's say, the blood is flowing in your mitral valve, okay? If the parameter here is high, let's say equal to 2, basically it's a Stokes flux type, okay? So a very mild action of the flux. If the parameter is low, basically you have a strong action of the flux. So it seems everything quite simple, but actually there is a strange phenomenon happening in the sense that if you run the simulation for several parameters, when the parameters reaches this value, 2 solutions actually are actually free, in the sense there is a symmetric mirror solution of the solution that is bifurcating. Here you see occurs. So basically there are 3 solutions, one that is the straight one and 2 that are wall-hugging solutions. So the flux can basically go up towards the wall of your mitral valve or go down towards the other wall of your mitral valve. And these occur for the same parameters, okay? From this parameter on, you will have always 3 solutions, okay? And this will be basically our definition of bifurcation, okay? So more solution coexisting for the same value of the parameter mu. Now, The wall-hugging solution phenomenon is actually something that you don't like in your heart because there are some recirculations that are asymmetric, and this can give you some problems about blood pressure and so on and so forth. But actually in nature, this is the physically stable solution. So you will find this solution in nature. And if you want to study this problem numerically, okay, mathematically, you can actually study the eigenvalue of your problem, in the sense that you linearize the system, you plot the eigenvalue like that, and you look at the real part of eigenvalue. This is the plot of real and complex plane of the eigenvalues, okay? And you look at the sign of the real part of eigenvalue, like the standard theory of the ODEs. And if the real eigenvalues are always negative, the solution is stable. And if the eigenvalues cross the zero, the solution is unstable. So in this case, we are in the wall-hugging solution. So as I said, the wall-hugging solution is stable, while this is the case of the straight flux. And this is the unstable solution, but actually is the solution that you would decide in your heart, okay? So there is a way to reach this configuration somehow without no bifurcation eventually. This was basically our question, our starting point. Now, remember, please keep in mind these plots, because I will talk about these plots a lot during the test cases. So I will refer to these plots like with the colorful plots or box plots, okay, depending on what is the feeling, let's say. So our question was, there's a way to reach the straight configuration, okay, without any type of bifurcation eventually, or somehow more naturally than the wall-hugging one. And we thought about optimal control, in the sense that optimal control is an input-output formulation pipeline here. So basically our question was, how can I change my inputs to achieve an optimal solution that is the straight flux, for example? And you see there is the PDE, but actually here you are adding information, like you add another variable that is called control that actually changes your solution in order to minimize a cost function that I will show you later. And then you add also a data. And in our case, the data will be, for example, the flux measurement of the flux in a portion of the domain. So we used optimal control as a strategy to drive our solution towards what we wanted to reach. And we studied several types of control, and we analyzed them. So let's move towards the framework formulation of our problem. And our problem is formulated to optimal control, as I said. So basically, parameterized optimal control. So basically, given a parameter in a parametric space and an observation in our observation domain, okay, so in a portion of the domain that I will call omega ops, and a forcing term, I want to find a pair now, a pair of state y and control u, which minimize a functional. Okay, now the functional is actually built in order to achieve our goal, in the sense that the state y, for example, in the Navier-Stokes case, is the velocity pressure field, okay? And the YD is represented by the Stokes flux. So basically here, I want to minimize the distance between the Stokes flux and the Navier-Stokes flux, okay? Basically paying the less I can with the control, okay? Now the control is weighted through a penalization parameter alpha that goes from, let's say, 0 to 1. And you can understand that if the alpha is maximum, so if alpha is equal to 1, you will control the system less, right? Because it weighs a lot on the functional minimization. While if alpha is very small, the norm of u can grow, and basically you will control a lot your system. Now, you want to minimize this functional subject to your state equation. This state equation is basically Navier-Stokes equation plus an operator of the control. So the state equation is given by a nonlinear a nonlinear equation here, okay, that has, you see, a nonlinear contribution and a linear contribution. And you have also the application, let's say, of a control operator here that acts on a portion of the domain omega u that is called control domain. Basically, it can be internal of in the domain, but also on the boundary, okay, and a forcing term. Now, there is a way to solve this problem, and it is basically called Lagrangian minimization. So I will define an arbitrary adjoint variable z, and this variable will change the formulation of our constrained minimization problem to an unconstrained one, in the sense that calling, okay, with X, the global space, and okay, yes, this sort of capital X, the global space, and X, the global variable here, given by the triplet of a state, control, and adjoint, you can build the Lagrangian functional, that is the sum of your functional plus, you see, this is actually a Lagrangian multiplier, let's say, it's like analysis 2, okay? This is your constraint, so your nonlinear constraint, in a weak formulation tested towards your adjoint variable. So to solve the minimization problem, you actually differentiate with respect to the three variables in order to achieve a system of three equations to solve, okay? And you find the optimal triplet. The first equation is called adjoint equation. Then you have the optimality condition here that links the adjoint with the control variable. And for sure, if you differentiate with respect to the adjoint variable, you will reach once again the constraint, okay? Now, we said that we wanted to understand what is the link of loss of uniqueness in the state equation with in the control framework, and actually the existence and the uniqueness of the control of the optimal control is strictly linked to the state equation. Okay, so now we need a tool, okay, a discretized tool, in order to study several solutions for several control and to understand if there are multiple solutions and their nature. The first thing that you do is basically to put yourself in a finite dimensional setting. So you use a discretization. Now we used finite element discretization, but I don't want to be detailed. I want to let you understand that basically everything becomes a huge matrix to be solved, okay, of this form. And actually there is a remark to say that basically the system is nonlinear, okay? The nonlinearity is present here in the state equation, but also in the adjoint equation, okay? Because you have a multiplication between the state variable y and the adjoint variable z, okay? So it's quadratically nonlinear in the state for the state equation, and for the adjoint equation, you have this multiplication. Now, if the system is nonlinear, usually you use some kind of linearization method to solve, okay, the problem numerically, and we use Newton's method. And okay, you define the residual, and basically this is the tangent method, but in a multidimensional framework. So you build the Jacobian and you solve this problem iteratively until you reach a convergence criterion, okay? Then actually now you are able to solve your problem for a specific parameter, but our goal was to solve our problem for lots of parameters in order to construct the bifurcation diagram. Okay, this is a pitchfork bifurcation diagram. So here there is mu equal to 2, so very Stokes type flow, and you have only a branch of solution, but then, as I said, around 0.96, you have three coexisting solutions here: the wall-hugging one and the straight one. Okay, now you need a algorithm that is capable to detect the bifurcation, but also to study the stability of the solution. Okay, and we decided to perform two stability analysis, okay? The one that is classic, the one of the controlled state equation, in the sense that we linearized Navier-Stokes equation, okay, with the information of the control inside in order to understand if the new controlled Navier-Stokes is stable or unstable in some parameters with some parametric features. So we studied the eigenvalues. If the eigenvalue is negative, we have a stable solution. If it's positive, you have the unstable solution, as I said. But we defined also a global eigenvalue analysis. Now, we were not sure about the meaning of this problem. We actually, there were and there are a lot of questions about this. Like, is it linked to physical stability, okay? Or it can give us information about also the presence of bifurcation. We had a lot of questions open at this point of the work. And this is the algorithm. And I don't want to go into the details, but you see that basically here you are solving your Navier-Stokes problem, starting from an initial guess, and you are following the parameter the parametric behavior recursively in order to capture the upper branch or the straight branch or the down branch, in the sense that while the step 8 and 9 helps you in understanding the stability features of your solutions, of your bifurcating solutions, the step from 1 to 6 helps you in finding the diagram. As I said, you need basically an algorithm that detects and is capable to draw for you the diagram, and that also study the stability. And this algorithm, the continuation algorithm, does the job. So let's start talking about the numerical results. And this is the general framework of all the numerical tests that we performed. So basically our goal was to recover a data, okay, given. In our case was a Stokes flux in the most of cases, let's say, or an asymmetric Navier-Stokes case taken in this line here that I call gamma ops, a line at the end of the domain. So as I said, our parameterized problem wants to minimize this functional, that is basically the distance between your optimal velocity with respect to the side flux, okay, paying the less I can. And now the control can be a forcing term, but actually can be also in the boundary condition. I will show you some example. And the example are actually presented from the weakest to the strongest. And I would say also to the strangest, you will see later. And for all the test cases, I will show you the numerical solution, the control action, and the behavior of the solutions. Here, I'm saying a natural behavior. I will be more specific about this adjective, natural, later. And then I will show you the eigenvalue analysis, both the global one that gives you information about the bifurcation point eventually, and also the state eigenvalue analysis, okay? The one that gives you information about the stability of your new controlled solution, okay? So let's start with the first example. The first example, it's a very typical example in numerical control, that is the Neumann control. So basically here, I'm controlling on gamma out how the flux is exiting the domain, okay? It's like you are putting some kind of valve and you are able to understand how the flux is exiting. And for this problem, we had a bifurcation in the sense that we were able to reconstruct the pitchfork diagram, okay? And here I'm presenting the controlled velocity fields, and you see that we have the Lagrangian solution, but also the straight one. But there is a difference with respect to the Navier-Stokes equation, because you have a diffusive action on gamma ops, in the sense now I'm presenting these plots in order to let you understand that we are actually controlling the system, okay? Because, for example, this is the this plot, okay? This is the wall-hugging plot, and this is the velocity, the magnitude of the velocity along gamma ops. And you see that actually the orange one is the controlled, so the uncontrolled is the green, and it's different, right? It's going somehow, we are going towards Stokes flux in the sense that it's more symmetric, as you see, okay? And it's more similar to the red one that is the symmetric uncontrolled solution, okay? So it's more similar to the straight one in this part of the domain, even if it is wall-hugging, okay? While for the straight one, we basically recovered the Navier-Stokes solution. This is only to let you understand that we are actually controlling the solution, okay? Even if we are seeing wall-hugging behavior. Now, this is the control plot. And the control plot is always very interesting because the control plot for the asymmetric solution, okay, is asymmetric, and you can imagine that. But also the control plot for the symmetric solution is asymmetric near the bifurcating point, the bifurcating parameter. You see here, this is the control over gamma out, okay, so at the end of the channel, for several parameters, okay? And near the bifurcating parameter, so here there is a 0.95, the control is highly asymmetric. Somehow, even if in the end you find the straight velocity field, the control is able to detect where the bifurcation point is, okay? And yes, here I'm actually defining the term natural, and we will define as natural branch the solution that you obtain through the algorithm, putting as initial guess the null function, okay? So it's the first one that you find without playing with the guesses, okay? And we were able to recover all the branches playing, as I said, with the guesses. If you play with the guesses in the algorithm, you can find all the branches, as I said, okay? But the first one that you find is the natural one. And in this case, the natural one was the wall-hugging one. Okay, so we are not changing a lot the system, okay? And the fact that we are not changing the system is seen also in the global eigenvalue analysis, and you will understand that if you do a comparison with respect to the eigenvalue analysis of the problem that will follow. So this is the global eigenvalue analysis. So we are plotting the real eigenvalue, okay, with respect to mu. The eigenvalues are always real because the linearized system of the optimal control problem is symmetric. Okay, so all the eigenvalues are real. And you see that there is this behavior here called that we call the shears. So basically you have two branches that are approaching to zero. They are approaching to zero. They never touch the zero, and then they go away together. And you see that the shears gives us information about the bifurcation point. Indeed, if you project, it is actually near 0.96, okay? 96. And okay, yes, some, let's say, remarks. If the problem is highly controlled, in the sense if alpha is smaller, you will see a lot of positive eigenvalues and a clustering of eigenvalues around the value of alpha. But then I will show you other plots later, and they will clarify this concept, okay? So highly controlled means a lot of positive eigenvalues. Now, as I told you, we performed also the state eigenvalue analysis. So you have to remember the colorful plot of Navier-Stokes with negative eigenvalues and negative positive eigenvalues. And in this case, we're the same. Okay, so I'm not showing them because actually we are not changing the stability. Okay, if you, in nature, if you find a problem controlled like we controlled that, it will give you basically the wall-hugging solution. Now, in order to understand better the features of the control, we perform also a distributed control. So a distributed control means that the control is a forcing term acting on the whole domain, okay? So it's like an external forcing term. It is not physical in this context because it's like playing, I don't know, with gravity, let's say, but it helped us a lot in understanding the features of the control system. Indeed, here I'm showing actually the control problem, okay? the control variable, sorry, and for the control variable with the target comparison, in the sense that in this case, to understand better how the problem worked, we put two different decide state. One that is the Stokes one, okay, and the other one that was the wall-hugging solution of Navier-Stokes, okay, for high Reynolds. And in any case, no matter the value of our parameter, we were able to recover the straight flux if we put inside the information about the Stokes flux, and the wall-hugging behavior if we put inside the information about Navier-Stokes, in the sense that even if for very let's say for high Reynolds, okay, so even if we are in a heart that pumps a lot of blood, we were able to recover a Stokes flux, okay, in the end. You see that basically orange line, that is the control symmetric velocity, and blue line, the Stokes velocity, that is the our decide state, is, I mean, they are coinciding, right? So we controlled a lot our system. And the same is for low Reynolds, so for blood that is flowing quite madly. And you see that basically we can recover a very strange behavior on gamma ops, in the sense that it's not symmetric. Okay, so we are controlling a lot the system, and this is due to the fact that the control here is strong because it works on the whole domain. Okay. Once again, here I'm plotting the control, and as I said, it is always slightly asymmetric also in the symmetric case, because it detects the parameter, okay, the bifurcation parameter. And in this case, it's the first time that actually we observe also an anticipation of the bifurcating phenomenon with respect to alpha. Okay, here is the plot of the upper branch, okay, bifurcation diagram. From low Reynolds to high Reynolds, let's say. And the uncontrolled is the dashed line. But you see, when you're controlling the system, you are actually pulling back the bifurcation point, okay? And the natural branch here is the one related to the data. So basically, if I put inside the Stokes information and I run my algorithm, I will find the straight solution naturally. While if I put inside the Navier-Stokes one, I will find the wall hugging. And this is a difference with respect to before, right? Because before we were not changing this natural behavior of the solution, okay? So now there is the global spectral analysis, and here there are no shears, but as you can see, as I anticipated you before, there are a lot of positive eigenvalues here in both the cases, okay? So I didn't say that before, but actually these global plots do not depend on what natural branches you are choosing. The one of before, the shears one, were the same both for the wall-hugging solution and for the straight solution, okay? And in this case, this is the same. The first two plots are for the straight solution, okay? So the Stokes decide state. And the bottom part is about the Navier-Stokes problem, okay? And you see that they are similar. And the shears are not appearing, but still you can understand when the bifurcation is occurring through the how the branches are approaching to zero, right? In this case, it's around 0.996 as before, but here it occurs earlier, okay? I'm not showing again the colorful plot, the box plot, because once again, unfortunately, they are the same of Navier-Stokes. So even in this case, even with the distributed control, we were not able to change the dynamic of the solution, okay? Now.
Sorry, Maria, can I ask you a question?
Yes.
But the blue eigenvalue of the slide before, this yes, one that do this strange behavior, are some special eigenvalues, or just you put it blue because they have this behavior? Why they're blue?
We just colored them as blue in order to let you understand the dynamic. You see, they are very strange with respect to the others, right? because they are the
yes,
one
yes,
that are
yes.
approaching to zero.
No, I thought there is a reason for which you detect in advance. No, you do the plot and
No.
then you see that there is
Yes.
this behavior.
Yes,
Ah,
exactly.
okay.
It's a post-processing
No, okay,
stuff,
okay,
let's
okay.
say.
Sorry, thanks.
No,
Okay.
don't worry, it's fine. And yes, now this problem we call the channel control. Okay, here we are talking again about the Stokes flux as a decide state. Okay, from now on, our decide state will be always the Stokes flux. And here we are putting like a concentrating forcing term on the line here, like we are somehow pushing or dilating, okay, the blood flow there. And once again, we put, as I said, the Stokes flux here as a decide state. And this is interesting because actually we found several solutions with respect to the value of alpha, in the sense that if your problem is not controlled much, okay, if your problem is not controlled much, in the sense if alpha is equal to 1, you will have the wall hugging solution. This is the adjoint velocity. Now I'm plotting several variables because I didn't want to show always, you know, the blood flow going up or stay straight. But here you see the adjoint velocity, okay? And it is asymmetric. So if your control is weak, you will always reach the wall hugging solution. While if you reduce the value of alpha, so if you control more your system, you will reach naturally the straight flux, okay? And I'm showing it in this plot. Basically, you see that if alpha is high, we are not changing our solution at all with this type of control, while if alpha is small, from the green line, that is the uncontrolled asymmetric velocity, we move towards the red line. You see that basically there is no difference between orange line and red line. So basically we are straightening, actually we are driving our solution towards the straight flux. Okay, once again, the control variables is always somehow asymmetric and detects the bifurcation point. And the natural branch in this case varies with respect to alpha, in the sense if alpha is high, so not very huge, I mean the control is weak, basically you will have the wall hugging solution, as I said, while if alpha is small, you will get naturally the straight solution. And in this case, it was very tough to build the bifurcation diagram. With the algorithm, as I said, you have to play with the initial guesses in order to find all the bifurcation diagram, okay? And here we had to work a lot with the initial guesses, very tailored one, in order to find the other branch, okay? So for the wall hugging, we have to play a lot in order to find the straight branch. And for the straight branch, it was a mess to find the wall hugging one, okay? But still the bifurcation was present and we knew that. And we knew that also from the usual eigenvalue global plot. Here you see we have the spectral analysis. As I said, it is the same for the straight plot and the wall hugging plot. And you see that there are the shears for the weak control, so for alpha equal to 1, but the shears somehow are broken then and disappear here. And you see that there are a lot of positive eigenvalue if alpha is decreasing, okay? So everything is consistent between the three numerical experiments, right? Okay, then you put the information in the state equation, okay? You linearize, you plot your bugs plot, the colorful plot, and they are the same as Navier-Stokes. So once again, let's say we failed in our initial goal, okay? But there's a but, because in the end, we built this problem here. This is the last test case, is the Dirichlet control. So basically here, the velocity can do whatever she wants, in the sense that can go out, but actually you can also inject velocity flux here, okay? In order to recover a Stokes flux on gamma ops as usual. And we actually found only one solution here, okay? We found this straight solution for even for very high alpha. Here the control variable cannot act a lot, but basically we found the straight solution. And this is the solution, okay, for very small alpha. Here you are controlling a lot your system, and as you see, you have a really Stokes type velocity here on gamma ops, okay? You see that it's actually a lot diffusive with respect to this other one, okay? But you have this strange behavior here, okay? Something like it's bifurcating like in the beginning of the channel. So it's a very strange behavior. But as I said, we were able to recover a straight flux, a Stokes type flux, even for high alpha. You see the orange line is equal to the violet line that is the symmetric velocity that the uncontrolled symmetric velocity. So high alpha is symmetric, but small alpha is really Stokes. Okay, so we recover totally our desired state. Okay, and this is the plot of the control. And as I said, basically for high value of alpha, it is pulling down velocity. So it's like the velocity is exiting from this orange line here, and it is avoiding the formation of asymmetric recirculation of blood that gives you the Volhagian behavior. So you actually obtain the straight flow because it is avoiding the recirculation, okay? And for high alpha, it happens that basically in order to recover this very diffusive behavior here, it puts inside a lot of flux in the sense that you see that the scale is quite high, okay? It's like the inlet here, more or less, okay? And it is, as I said, asymmetric, okay? So it detects, once again, something wrong in the system, okay? And this asymmetry actually reflects in the velocity field here, okay? And now you see the eigenvalue plot, the global eigenvalue analysis. And this was the strangest, right? Because there are no shears, there are no broken shears, all the eigenvalues are positive. So it's like I'm controlling a lot the system, but still there is, let's say, you are losing the information about where the bifurcation is happening. For high alpha, for example, there are no eigenvalues approaching to zero, at least not the blue one that we processed. But you see that something very strange is happening here, because it's the first time that we see eigenvalues of the optimal control problem crossing the origin. This never happened. Even with the shears, as I told you, the shears approach to zero, but then they are pulled away. In this case, we have a crossing of the origin, okay? And in this case, we had that very strange solution, okay, with the bifurcating phenomena near the inlet channel, okay? And now I can actually show you the plot, the colorful plot, the Bugs plot. Now here on the top, these are the uncontrolled Navier-Stokes, so the one that you saw in the beginning of the talk. And this is the Volhagian solution for uncontrolled Navier-Stokes. This is the asymmetric solution, the asymmetric solution for the problem of the shape problem, okay? So you see that the asymmetric solution of the shape problem is unstable in this case. It's not stable like Navier-Stokes, it's unstable because there are real eigenvalues that are crossing the origin. Now, this is the straight solution for uncontrolled Navier-Stokes, and this is the straight solution for the controlled one, and you see that everything is below zero, right? So all the eigenvalues are negative, and the solution seems to be stable. Now, something very strange is happening here, okay? Because in the very strange plot, the one with the lower alpha, so the one with that bifurcating phenomena in the inlet channel, also complex eigenvalues are crossing the origin. So actually, we are not talking about a pitchfork bifurcation. Maybe we are in the regime of bifurcation, but this is an open question for us. We actually don't know. So there is a lot to study in this test case, okay? Okay, this is actually our last slide about the numerical results. Here, there is let's say, a recap of what I've said about the global eigenvalue analysis of all the plot. I want only to stress a thing, that basically you can recover in post-processing what is the behavior of your solution, if it is symmetric or asymmetric, from a very tailored, let's say, eigenvalue plot. This is the eigenvalue plot of the state equation plus the adjoint equation linearized. And if you have these very symmetric shears, the solution is the wall hugging one. While if you have these strange shears here, you have a straight solution. So basically you can recover the solution features also from this eigenvalue plot. Now, let's talk a little bit about model order reduction. And this is the last part of the talk, so it's almost finished. And model order reduction in this case can be very useful in the sense that optimal control problems are usually very expensive, because you don't have to solve only one equation, you have to solve three equations. And in this kind of formulation of bifurcating phenomena, actually you have to solve your problem for a lot of parameters in order to recover the bifurcation diagram, right? So you want somehow to exploit the hidden parametric structure of the problem, okay? And reduced order model helps you to do that, okay? Indeed, reduced order modeling is based on an approximation of the approximation. As I said, we used finite element, but this is a general argument, in the sense that you have your continuous solution here, in our case can be state, control, or adjoint. You use a discretization that has dimension capital calligraphic N, okay? And assuming that this discretization is a good discretization of your continuous variable, you can apply another discretization of dimension capital N. And the important thing is that capital N is much lower than calligraphic N. So that basically your linear system, the system that you are going to solve, it's in a low dimensional framework with respect to the previous one, but still you don't want to lose the accuracy, okay? I don't want to be specific here, but we use proper orthogonal decomposition that is basically a compression algorithm. So you, let's say, look to a very specific finite element solution that we call snapshot, and you try to recover the most of the information given by this finite element solution, and basically solving an eigenvalue problem on the covariance matrix of the snapshot and retaining the n largest eigenvalue. Okay, so you choose basically the value of n, and this n is much lower than capital N, okay? And you build the basis as linear combination of these snapshots. Now, with optimal control is a bit more complicated, because the matrix that you are solving has a very particular, let's say, structure that is a saddle point structure, in the sense that this is the Jacobian matrix of the optimal control, okay? So in the Newton solver, you will solve at each iteration a matrix like that. You will have a matrix like that at each iteration. And this matrix is called the saddle point matrix. And in order to have a well-posed system, you can prove the well-posedness through these three hypotheses. So the bilinear form related to the matrix A and the bilinear form related to the matrix B has to be continuous, and it derives from the previous discretization, as well as the coercivity of A over the kernel of B. But still there is an issue, that is the stability issue of the matrix B, okay, that has to verify this hypothesis here of insubstability. And this is provable when the state space that here I call Yn is equal to the adjoint space that here I call Qn. And in reduced spaces, this is not the case when you use POD, even if your adjoint and state snapshot are taken with the same discretization technique. So we use aggregated spaces, and then we use also supermiser for velocity because we were dealing with Navier-Stokes, but this is another story. Then we define basically, in order to have this IMSUP condition verified, a common space for state and adjoint given by the linear combination of the two variables for both the spaces, okay, while we use standard POD for the control. Okay, last slide of results. I'm not putting the variables here because, I mean, they were the same like the one that I showed you before. Here we have two types of plots, of error plots. This is, and I'm plotting actually the easiest case, so the Neumann control on the top, and the worst case that we had, that is the last one, so the Dirichlet control with the strange behavior in the inlet channel. And as you see with the Neumann control, even with few bases, we were able to have very good average relative error for all the variables, while with the Dirichlet control, we were struggling a little bit with the adjoint and the control variable, but still the state variables are okay. But it is more interesting, I think, look at these plots here. So basically this plot is about the relative error with respect to the variable mu. So I'm not averaging anything. I'm putting n equal to 20, and I'm showing varying mu how it is the relative error. And it is very interesting because the peaks in the error gives you information about the bifurcation point. In the sense, this is the Neumann control, so the weaker one. And you see that there is this peak that is actually not really, I mean, a huge peak, since you see the scale here is 10 to the minus 8. But the peak here is around 0.96, exactly the bifurcation point. While for the Dirichlet case, the strangest one, as I said, there is no clue about any type of bifurcation here, but there is a clue of something going wrong here at the end, because exactly at the end you had that strange behavior in the inlet channel. So, okay, I don't want to go through the conclusion because actually it's a recap of what we did together, but I want to underline a little bit the perspective because there is a lot to do about the Dirichlet problem. It's actually an open question, and we are interested in understand, even if some of you know something, please contact me, tell me. And maybe another interesting thing is to study how the time dependency can somehow interact with the bifurcating phenomena given by the parameters. So I hope you enjoyed this talk as I enjoyed working at this stuff. Thank you.
Thank you, Maria, a lot for your seminar. Now it's
Thank
the
you.
moment for questions. You can unmute yourself and ask directly. Actually, I have a question. Why did you decide at the beginning to study the stationary Navier-Stokes equation? It's more difficult numerically to study the time-dependent one.
I mean, we decided to study the steady Navier-Stokes equation actually because we knew the theory of uncontrolled Navier-Stokes equation with respect to the steady one, okay? Or the theory about the pitchfork bifurcation depending on the parameter mu. In literature, we had it about steady Navier-Stokes. But actually now we are interested also in time dependency, because for sure there are bifurcation arising from the time independently with respect to the parameter. So it would be nice also to understand that. So only how the time changes this behavior of the bifurcation phenomena, but maybe it could be very interesting to put them together. So it was only a first step due to the fact that we knew how it worked in literature for the state equation, the uncontrolled one.
Okay, thanks.
Welcome.
Another thing, I was a bit confused by the graph in the plots, sorry, in which you plot on the x-axis x2 and the y-axis the control magnitude. You did it all the time for all the type of controls.
Like this one.
It's not clear to me what it means that for some value of mu, the plot is symmetric.
Okay, here.
So, what do you detect? Why? It's not very clear to me.
Okay. This is the Neumann control, okay? So the one where you are controlling how the flux is going out here, okay?
Yeah.
Now, here I'm plotting the magnitude of the control, okay? So actually the value of the normal derivative of the velocity, okay, plus the pressure field. Now, this is the asymmetric solution, okay? So this is the plot of the control with respect to this plot.
Okay.
So I'm actually plotting the Neumann condition here, okay? And this is asymmetric, always asymmetric, okay? For all the value of the parameters. And you are expecting that because you are reaching an asymmetric behavior, right? So you expect that basically your flux is going asymmetrically out, right?
Yes.
Oh, yes, okay. Now this is the plot
Of the symmetric.
of the symmetric one, exactly. Now you see that when mu is equal to 2, so when you are at the beginning, right, of your bifurcation diagram, so when you have only a Stokes-type flux, right, you have no control. It's actually 0, okay? If you decrease the value of your parameter, it happens that near the value of the parameter of the bifurcation parameter, you have a strong asymmetry. Really here, you see, this is the blue line, and it touches 0.8 on the left, and it's only 0.4, so the half on the right.
What's the meaning? What's the meaning of for this value of mu in the symmetric case? Why this plot is asymmetric?
This plot is asymmetric. I mean, the explanation that we give is like, okay, the velocity field, it's always symmetric, but somehow the global solution has to understand that something is going, that the velocity field wants to go up, because naturally it wants to go up. So in order to do so, it's somehow driving asymmetrically the natural asymmetric behavior in order to let it straight, right? I don't know if it's clear.
Okay, it's like you push to the center of the tube to
yes,
to be symmetric.
Exactly. So in order to be the solution symmetric, you actually have to act asymmetrically on it because it is naturally asymmetric.
Okay. Yeah.
Okay. And this always happens. So the global solution actually, it's able to detect when something strange is happening. Okay. So while from the velocity field, you are not able to understand if a bifurcating phenomena is happening, because if you run a simulation and the simulation is straight, okay, so you don't have the, you don't have the information about the upper part, okay? You run a simulation and the simulation is straight. From the velocity field, you cannot say, okay, something strange is happening. But if you look at the control variable, you always can understand that there is something strange happening around this kind of parameter, right? So
but still, for mu equal to 1, you expect to be in the bifurcating, how do you say, regime?
Yes, say. Exactly. And this is
already.
Yes, and it is asymmetric too.
As soon as you see the graph of something, it's not important to be symmetric. It's just not 0. If you see that you are acting like for mu equal to 1, you are already in the bifurcating regime.
Exactly. You are already in the bifurcating regime, but your solution is the straight one.
Okay.
Right?
Okay. Yeah. Yes.
So you cannot detect if there is a bifurcation, while from the control plot you can detect it.
Okay. Yes. Thank you.
I mean, this is only numerical experience, right? We actually, there's no.
No. Okay. No, I didn't know how to interpret this picture. So yeah. Okay. Thanks.
And I hope it is clear now.
Mm-hmm.
Okay. You're welcome.
Okay. So it seems to me that there are no more questions. So I propose to thank, let's see, yes, to thank Maria again. And
thank you.
we meet as usual, Maria, next
Next Friday. Thank you. Thank you all.
Bye. Thank you.